All right, so good morning and welcome to this video solution on semiconductors. This is from NCRT, very important one. I will not restrict the discussion to the question only. I will explain you some more things which you can already see on the screen and you will get to know some interesting facts. Okay, so what is the question? The question is if you have carbon, silicon, and germanium, they have four valence electrons. Okay, and they're characterized by valence and conduction bands. Okay, you know what are valence and conduction bands? Separated by an energy band gap. Okay, so the key word here is energy band gap, and it is represented by, this is for carbon, this is for silicon, and this is for germanium. You have to identify the the true one, right? So you have to identify the true statement. So we have to organize the energy band gaps based on the values we know and the reasoning we know. Okay, so this definitely is a tricky question, but I'll give you some more deep insight into the answer. So this is your carbon. Okay, in the periodic table, if you see, okay, if you notice the periodic table, you have something like a group 4, right? The group 4 where you see all these, right? You see uh, carbon, then you see silicon, you see germanium. Okay, these are the most versatile uh, semiconductors you see in nature. Okay, especially these two. Okay, so group 4, and the number of valence electrons they have is 4, which is already mentioned. So they have 4 valence electrons. This is very good to know information. 4 valence electrons. Okay. Now, another interesting fact is that these all three, they cannot create ionic bonds. So ionic bonds are not possible. Ionic bonds are not possible because the external electrons, which are 4, the valence 4 electrons, it is way too difficult to leave the the shells and get rid of the electron and transfer, which is what is required for ionic bonds. So ionic bonds are not possible. It will create too much imbalance. You cannot. You can have valence ionic bonds being created using 1, 2, 3 electrons, but getting rid of 4 valence electrons is way too difficult. So ionic bonds are not possible. Okay, you cannot have ionic bonds for these group 4 elements. All right, the only choice you have is the choice of the covalent bond, which is what is called as the covalent bonds, which are sharing of electrons, right? Sharing. All right, the outside, the ones which are in the external quantum state of KLM, and if you know a bit of chemistry. So, so the first one you see, okay, this diagram is carbon, this is silicon, and this is germanium. Okay, so when I have written the electronic configurations, this electronic configuration side is the ground state. Okay, this is the ground state when you have an individual carbon atom, an individual silicon atom, and a germanium carbon atom. All of them will be in the ground state. But the moment they form a covalent bond, when the covalent bond is formed, okay, now the covalent bond is getting created. When the covalent bond is getting created, the this state is where the covalent bond has got created, and there is a reorganization. So if you see the electron here, 2 has become 1, and there is an increase on this side. Okay, so you see this is 3s2, 3p3, and now s has got reduced by 1 and p has one more added to it. So this is s2 and this is s1. So if you notice, in the covalent bond state where the silicon, for example, creates bonds with the neighboring structure, right? So you would have seen this structure where you have a silicon and it creates a bond with a neighboring one, This is another silicon, and it creates one more bond, silicon, and this is silicon, and this is silicon. Okay, so you can see the bond when this structure is formed, which we call as a crystal structure. Okay, it's a tetrahedral structure. Okay, the tetrahedral structure, right? And if you notice this sp3, in the end, so this is sp3. If you notice the last two, this is also sp3. Okay, and this is also sp3, right? Now, so I hope you've come to know some interesting points about that. When you have covalent bonds being created, the state changes from ground state to the covalent bond state. Okay, so this is the new state that gets created. This is one. Now, if you see, purely from the standpoint of energy band gap, okay, the energy band gap, carbon carbon is not considered a semiconductor, is not a semiconductor. Okay, this is something you must know. The reason is carbon, even if you're able to create the covalent bonds, just like you're able to create the covalent bond for silicon and germanium, to this point, all of them look same, right? So if you do this if you just look into these two diagrams, even carbon appears to be a semiconductor because it is pretty similar to the the electronic configuration you see for silicon and germanium. It is also sp3. So don't be under the impression that carbon is a semiconductor. Carbon is still not a semiconductor. The reason is when you give carbon a lot of temperature, which is try to make it a conductor, by giving it, for example, room temperature and higher, it is not possible to break the covalent bond. So carbon, you can't break the covalent bond. You can't break the covalent bonds, which means that the valence electrons, which means that the valence electrons, cannot jump to conduction band, right? Conduction cannot jump to conduction band. Conduction band. It is not possible for carbon uh, atoms to exhibit this. So carbon is not a semiconductor. And then carbon, incidentally, if you talk about carbon, we'll talk a bit more about carbon. Carbon is existing in many formats, right? So when carbon is existing as graphite, right, it behaves like a metal because it's a very good conductor. Now this is behaving like a metal, okay? And metals, don't have any energy band gaps. When we talk about the gap between the conduction band, and I hope this diagram is known to you, that this is your conduction band, then there is a gap between the valence band, conduction band, this is your valence band, and this is your forbidden energy gap, right? So in the case of metal, this does not exist. And in the case of insulators, it is very high. In the case of semiconductors, the range is very small. So in the case of carbon, the energy gap, if you see graphite, when it exists as a graphite, it behaves like a metal. But diamond, when it becomes diamond, it behaves like insulator. The energy gap is to the tune of 6 electron volts. Okay, so carbon is not even to be considered the part of semiconductor family, even though it belongs to group 4. Okay, it belongs to group 4. So some important aspects which you must know. You can be asked many questions on carbon itself. So you should be mentally ready. You should know a lot about carbon also. Why carbon is not a semiconductor? Because carbon occurs in different formats, and breaking the covalent bonds of carbon at room temperature with very small type of temperature, 300 Kelvin, it is not possible to break the bonds and make the electrons jump from valence band to the conduction band. So in carbon, this process is not possible. Now let's talk about silicon. Okay, silicon is a very versatile type of semiconductor, and so is germanium. And if you notice silicon, the number of, the so silicon has KLM, right? So KLM, if you see the quantum number 3, and in the case of the germanium, the quantum number is 4, right? So the electrons which are there in the case of the germanium, they are at an outer level, and therefore their energies are lower. Okay, so you remember that each electron will occupy a different energy level. The energy level which is occupied in the case of germanium vis-a-vis silicon is low, which means the interaction with nucleus is weak. When I say the energy is low, I mean the interaction with nucleus is low because it is outside, right? So the nucleus is at the center. You have one, then you have two, then you have three, and then you have four, right? So if you have SPDF formation in the fourth one, it is far away. So the interaction with nucleus is low. So if you look into the energy band gap of germanium. All right, so if you talk about the energy band gap for silicon, it is to the tune of zero point 0.7 electron volt. That's all. Okay, so this is zero point 0.7 electron volts, and that for germanium is 1.12 electron volts. So if I were to write the values in an ascending order, the carbon is 6 electron volts, practically an insulator. Then it is followed by germanium. Okay, this is 1.12, and then which is greater than silicon, which is 0 0.7 electron volts. Okay, so these two, this is a so just write silicon here. Okay, silicon, and silicon is 0 0.7 electron volts. Okay, so this is silicon. So if you go back to the choices, you can see that the silicon is less than germanium. Okay, the silicon is less than germanium. So choice number A is the correct choice. Okay, so if you see this, I have told you more than what is required, but it is important for you to understand the big picture. A lot of students are confused and start believing that carbon is also a semiconductor. I hope that myth is broken. And once you have, the silicon and germanium, these are able to produce electron and hole pair at room temperature also. So if this is your room temperature, and I draw the valence band, the gap is so small for silicon and germanium, around 1 electron volt approximately, that the electrons leave from the valence band, leave behind holes. So the holes are created here in the valence band, and the electrons jump only from the valence band to this, and you will see a lot of electrons here, right? So this jumping thing which has happened, from, so holes are left behind, holes, and these are electrons. Okay, so this is the electron hole formation, and the band gap you can see is very small for semiconductor. Approximately we say it's 1 electron volt. So I hope you found this video suitable and it gave you more knowledge, and you can compare this to any other YouTube channel, website. Nobody will give you this level of detail about the even the basics of semiconductors. So thank you very much. Please do not forget to subscribe to my channel. It already has 2000 videos. You can go through them, short videos, long videos, conceptual videos, solve numerical problems. Almost a complete physics is available. All you need is focus. All you need is a drive to be successful. All the best to you and wait for my next video. Thank you very much.